Yo, welcome back. All right, here we go. We are going to play off of what we proved in our last video, right? So we actually proved that the limit of sine x over x as x went to 0 is 1. So we did a whole big squeeze theorem proof. And we proved that the limit of sine x over x as x goes to 0 is 1. And we talked about, turns out that this variable doesn't really matter. It could be sine w over w, sine y over y, sine ax over ax. Notice how these are identical. And we're driving ax, or in this case, x to 0, which would drive ax to 0. Or it could be sine of some function over that exact function. And if we can drive that function to 0, we're always going to get 1. It always works out to be that way. All right, so let's see how these problems play out. But before we do that, a couple of generalizations. So what about the limit of sine 3x over x as x goes to 0? Right? That's not exactly sine x over x, right? And if you're following this here, it looks like that this has to be the same. So this really has to be a 3 down here, and it's not. So you're like, all right, well, then why don't you put a 3 there? So in other words, I could do the limit of sine of 3x over, and I'm going to go ahead and I'm going to put myself a 3 here. So why not, right? So if I'm going to put a 3 there, I'm really dividing this expression by 3. I have to undo that. I can multiply by 3. So it's like I'm multiplying that fraction by 1. So I'm really not doing anything, right? I'm just kind of multiplying by 1, and that's cool. So now this particular 3 up top, I'm going to pull out because I'm allowed to pull constants through limits. That's one of our properties. So I get the limit as x goes to 0 of sine of 3x over 3x. And now it fits this form of sine of box over box as box is driven to 0. Well, that's going to be 1. So all of that is 1. So I get 3 times 1, which is 3. And you could probably generalize. You don't need to do this every time. You can just kind of memorize that. All right, let's say for any constant a, if I have the limit of sine ax over x as x goes to 0, what do you think the answer is? All right, pause the video, see if you can figure it out. When you come back, hopefully you say a, okay? So that's it. So sine of 7x over x goes to 0, limit would be just 7. And you can do that. You could just write the answer. You don't actually have to do this little, arithmetic manipulation that we did here. All right, so that's pretty cool. All right, there's a couple more of these generalizations that we want to look at. So let's go down and put up 2 and 3 on here. All right, so what would I do with this next guy? So again, issue is that these have to be identical. It's got to be sine 5y over 5y to use the generalization up top that we discussed. So first thing I do is I get rid of this 7. So this is not really 7. It's like 1/7 times all of this. So I can pull out this 1/7 like that, right? Limit as y goes to 0 of sine of 5y over y, right? But again, this needs to be a 5 here. So just like before, I can do the same exact trick, just divide by 5, but then undo it right away. So you're like multiplying that fraction by 1. And then what I can now do is say, all right, well, this 5 up top, I'm going to pull out. 5 times a 7th, that's 5/7. And then I'm going to get limit as y goes to 0 of sine of 5y over 5y. And there I have that little pattern I saw before. This limit, I should know, is going to be 1, right? Limit of sine box over box as box is driven to 0. That's going to be 1. So you get 5/7 times 1, so it's 5/7. Again, no real need to show work like this. I love this for note flow, but maybe you can see the pattern, right? What do you think the limit of sine ax over bx as x goes to 0 would be, right? It would be a over b. And you can say that if you get a problem like that. All right. This one's a little bit more bananas, but not too crazy. So I'll kind of walk you through this one a little bit quicker. All right, so I can rewrite this guy as the limit as x goes to 0. And watch what I do here. I'm going to do sine of 2x over something times something over sine of 3x. Okay? And so now what do I need to have going on here? I'm going to use all sorts of colors for this. Well, the first thing I need is if I'm going to apply this rule that I applied before in the others, I'm going to need an x here down here, right? So I need an x there, and I'm also going to need an x here. So, okay, so you just multiply by x over x. So that's not changing the problem, so that's good. All right, the other thing that I'm going to need, right, if for this guy, this is sine 2x over, this has got to be a 2. So you're like, all right, so then just divide by 2. Well, then I'm going to have to multiply by 2. But just like before, right, What do you think I'm going to do with that 2? Well, maybe this time I'll pull it out right away. All right, so that 2 comes out right away. Now, what about this particular expression over here? Well, all right, I need this up here not to be x, but to be 3x. It's got to match it exactly. So if I'm going to multiply by 3, I'd have to divide by 3 to undo that. So again, that's like 1/3 down here. I'll just pull that out, and I'll get this 2/3 out in front. And so now what I have, it's a little bit more bananas, but I have the limit of a product. And the limit of a product is the product of the limits, right? So I'll take my time here. So I can write this as 2/3 limit of sine of 2x over 2x as x goes to 0 times limit of 3x over sine of 3x as x goes to 0. And this limit here fits the mold. Limit of sine of box over box as box goes to 0, that's going to be 1. This guy also fits the mold, although I didn't specifically discuss it, right? If you invert this, and you can actually see it in the squeeze theorem proof of this, it's not going to change your answer. You're still going to get 1 when you do the limit if this is flipped. So limit of box over sine of box as box gets driven to 0, that's also going to be 1. So 2/3 times 1 is going to be 2/3. And again, the quick generalization here is, all right, well, I don't ever want to have to do that ever again, right? If I see the limit of sine AX over sine BX as x goes to 0, yes, I can just say that it's equal to A over B. So these generalizations are going to help us do some other types of limit problems. So let's do what I'm talking about here, all right? So here we go. It says the key is to find the limit we proved the squeeze theorem embedded in the problem. So in other words, the limit of sine x over x as x goes to 0. You want to kind of see that somehow embedded in the problem and then kind of extract it using properties of limits. So like right here, I see sine x over x. I see that. It's embedded in the problem. But this, I can't just pull that out, so to speak, because there's this x plus here. So what is it that I can do? Well, you know a couple of things, right? You know that fractions can be broken up over addition, or in other words, this x can divide both this and this. So I'm going to rewrite this expression. And this is in calculus, by the way. This is pre-calculus. I'm just rewriting this as x over x plus 2 sine x over x. And really all I did is I added fractions in reverse, or I undid adding fractions. I decomposed them. Think about it. If you're going to add these two fractions, they have the same denominator. You'd keep the denominator at the top, so you'd get this. So you just kind of like reverse added fractions, if that's even a thing. So now why did I do that? Well, because now I have a limit of a sum. And the limit of a sum is the sum of the limits. So I can write this as the limit as x goes to 0 of the first part of this sum, but x over x, last time I checked, that's 1. Plus the second part of this sum, oh, by the way, this 2, you could get moved through this second limit. So it'd be 2 limit of sine x over x as x goes to 0. So I kind of did a little arithmetic here. I can't speak. A little simplification here, right? Basically decompose fractions, and I use limit properties. All right, and the idea was when I did all of that, I kind of extracted or just kind of found that limit that we proved. And you're not doing this by direct substitution. You're doing this by memorization. We took about a 20-minute video to figure out that the limit of this was equal to 1. So now we can just say it's 1. We don't have to ever prove it again. So I'm going to get the limit of 1 as x goes to 0. That's just 1. Plus 2 times this is just 1. So you end up getting 3 here. All right. Again, the key is to see the limit of sine x over x as x goes to 0, to see that somewhere in the problem. In fact, you might also see this guy, which we talked about a little while ago, which that's also equal to 1. See that somewhere in the problem. All right, let's take a look at the next problem here. Next problem, not as bad. All right, so you get limit of sine cubed x over x. So again, if you tried to directly substitute, you'd get sine of 0 over 0. So it wouldn't work. You get an indeterminate form. So you got to try something. So the something to try here is to rewrite this. Like, how would I rewrite this? Well, you're looking for sine x over x. So you're like, all right, well, let me just rewrite limit as x goes to 0. And now I need to write this. So I'm going to write that. So then what would I have to multiply this by so that it was equivalent to that? Hopefully you're saying sine squared x, right? So that's what you get. So now you're like, all right, so what's the story with that? Well, limit of a product is the product of the limits. So I can write this as the limit of sine x over x as x goes to 0 times the limit of sine squared x which, by the way, just for note flow, I'm going to rewrite it to what it means. It means sine x quantity squared as x goes to 0. So this here means that there, but you knew that. So now why is this a good thing? Well, here we go again. This guy we already proved. We know that that's 1. The other one we can actually do, right? I can chuck 0 in for x. The sine of 0 is 0. 0 squared is 0. So I get 1 times 0 here. So this limit ends up being 0. But again, I rewrote the expression to extract that known limit that we painstakingly solved using the squeeze theorem. All right, let's take a look at this one. You might want even to pause the video and see if you can do it on your own, right? You'd certainly see the sine x up here, and there's an x here and an x squared, but you can't break up fractions over subtraction, right? You know, if that was the case, then when you subtracted fractions, you would subtract denominators too, and that's obviously not true. So what is it you can do here? Well, hopefully you're thinking, you know what, let me factor the bottom. And I could actually pull out a 2x in the bottom, you know, but you know what? I don't think I want to. I'm just going to pull out an x. Not that it matters, but I'm going to pull out just an x. And then I'm going to get 4 minus 2x, right? X times 4, 4x, x times minus 2x squared. All right, so we get that. So you're like, all right, so how did that help you? Well, now you got this x connected with multiplication. So you can break up fractions over multiplication a lot easier, right? So I can rewrite this now. Again, I'm not taking the limit. I'm just writing that along. I can rewrite this as sine x over x times 1 over 4 minus 2x. And you should take a second and pause and be like, yeah, that makes sense, because when you multiply fractions, you multiply across the top and the bottom. Sine x times 1 is sine x, and x times 4 minus 2x is that, x times 4 minus 2x. So now why did I do that? Well, because now I have the limit of a product. And what is the limit of a product? Product of the limits. So I get the limit as x goes to 0 of sine x over x. There it is. It's safely been extracted, right? Times the limit as x goes to 0 of 1 over 4 minus 2x. And so now what is the story here? Well, this is 1, right? That's why we did that before. This you can directly substitute. So if I go ahead and directly substitute here, 4 minus 2 times 0, that's just going to be 4 minus 0. That's going to be 4. I'm going to get times a fourth. My answer here is going to be 1/4. Okay? But again, the whole idea is to simplify so that you can pull out that known limit. All right, let's do one more. So let's scroll up, take this over. This is a pretty good one. This is going to be one that eventually you actually also could memorize. Back in the day, we memorized these a lot more. They don't necessarily harp on this too much anymore nowadays. But this is one when I took calculus forever ago. They told me to memorize. But before you can memorize it, we got to derive it. So you know why I like to do this problem, though? It's because I had mentioned how to do this in class, but we never did one like it. So in other words, all right, how would you do this limit? You don't see sine anywhere, right? There's no sine x over x. You're like, why does this even fall into this category? Well, all right, directly substitute. Cosine of 0 is 1. 1 minus 1 is 0, right? And then over 0, you get an indeterminate form. So now what are the things you can try here? You're not going to factor, although I mean you might think to factor, but factoring is not going to go for it. There are no fractions to add. There's no binomial to expand. So does anyone remember what I said, which usually applies to radicals, but if you have a binomial trig function, that you can use that as well? Hopefully you are saying, Frank, did you hear that? Frank, was that you? Yes, Frank, very good. Conjugate, right? I can actually multiply by the conjugate here. So I'm going to multiply the top of this fraction by cosine x plus 1. That would be the conjugate of that numerator over itself. Now, when I say multiply the conjugate, I'm really multiplying by the conjugate over itself. So I'm really multiplying by 1. So that's why I'm allowed to do this. Now, why in the world would this help me, right? Well, let's find out. So if I distribute up top, I get cosine x times cosine x. That's cosine squared x. What happens when you multiply conjugates? The outer and the inner products will sum to 0. So we don't need to be heroes and write that. We're just not going to write anything. And then we have -1 times +1. That's -1. The bottom would behoove us to leave it as x times cosine x plus 1. So don't be a hero. Don't distribute. And you get the limit as x goes to 0. Now, normally when we did this conjugate stuff with radicals, the radical went away. So why would you do it now? Well, take a look at what you got here. up top, you just created a Pythagorean, I can't speak, a Pythagorean identity, right? Do you remember the big dog identity? Sine squared x plus cosine squared x equals 1. If you're going to remember anyone, that's the one you remember. So now if I subtract both sides by cosine squared x, I get sine squared x equals 1 minus cosine squared x. You're like, holy cow, I can replace this blue box with what it's equal to, which is sine squared x. All right. And I'm doing it in blue so you can really see. All right. So you get the limit as x goes to 0. The identity is used there. And then here you get this. So now here's the deal. Now you're like, oh, now I get why you put it in the section. Now I see this sine x over x stuff. Do you see that limit that you need to extract? I can decompose this fraction. I can write this as the limit as x goes to 0 of sine x over x times sine x over cosine x plus 1. That's me breaking up the fraction using my knowledge of, 7th and 8th grade multiplication. If I multiply across here, I get sine squared x. If I multiply across here, I get this. So now what do I have? I have the limit of a product. And guess what? That's the product of the limit. So this is the limit as x goes to 0 of sine x over x times the limit as x goes to 0 of sine x over cosine x plus 1. So what's the story here? All right. Well, it turns out that this is just equal to 1, right? We've said that a bazillion times in this video so far. And this, hopefully we can do. You're going to get sine of 0. Uh-oh, getting nervous now, right? That's going to be 0 over cosine of 0 plus 1. Well, that's 1 plus 1. That's 2. This is not a problem. 0 divided by 2 is 0. So 1 times 0 is 0. And so it turns out that this limit here is just 0. And that's us using the conjugate with trig functions, which is really, really neat. All right. So if I kind of scroll down to this little box, Mrs. Haas put this, oh, what happened there? Oh, we don't want to do that. All right. Mrs. Haas put this nice little box here and said, hey, these are the limits we want you to memorize. So the sine x over x1, the x over sine x, right? As x over 0, that limit is 1. This is how my teacher used to make us memorize this, right? He's like, that limit, hold on here. Oh, we froze a little bit. This limit is 1. It's, I've frozen. All right, that's all right. No big deal. See the 1 here? See the 1? Oh, there it is. All right, this limit is 1, right? So stupid. And then this limit is 0. All right, again, dumb, but whatever, if it helps you remember it. But now understand that if this changes, if that's anything but as x goes to 0, then obviously this isn't true. Regardless of how you want to memorize it, it would help you to remember it. But hopefully you understand where it came from. All right, so that's that, and we'll see you soon. See you.